So in this lecture we will be designing our beams for shear. We will discuss both IS 456 and SP 16 methods. So my design stipulations are: beam size 200 by 500 millimeter, FCK grade of concrete 25 Newton per millimeter square, grade of steel Fy it is 500 Newton per millimeter square, clear cover it is 25 mm. So mu, which is analysis moment from ETAPS at ultimate load combinations. So moment will be 130 kilonewton meters. So and it will be 130 into 10 power 6 Newton millimeter. So this is analysis moment. And my analysis shear, so VU from ETAPS at ultimate load combinations, so it is 120 kilonewton. So it will be 120 into 10 power 3 Newton. So this is analysis moment mu, and this is analysis shear. Clear? So from my flexure design, AST required it is 796 mm square. AST requirement 769 mm square. So I provided a steel of 800 mm square. 800 mm square. How it is provided? I provided 4 numbers of 16 mm dia. Here mu is support moment. Or hogging moment. So you please remember, for support or hogging moment, the steel will be provided at the top. So this 800 mm square, it will be provided at top, because your mu is hogging moment or it is support moment. If it was the sagging or span moment, then it will be provided at bottom. Clear? So my width of the beam it is 200 millimeter. Total depth of the beam it is 500 millimeter, whereas the effective depth, so D will be 500 minus so cover 25 plus diameter of stirrup 8 and these four numbers of 16 mm dia are placed in two layers. So if it was the case, so then 16 plus 16 by 2. So let me calculate the effective depth. 500 minus 25 plus 8 plus 16 plus again 16 by 2, it is 8. So it is 443. So effective depth will be 443 mm. So this is the effective depth. (443 millimeters). Okay. So in this case, our first step will be shear stress due to the shear force. We need to calculate shear stress due to the shear force. So for which you can refer IS 456 2000, page number 72. So clause 40.1, or you can refer SP16 page number 175, clause 4.2, the same formula available. So it is tau V equals VU divided by BD. So let me check the code. So I will open IS 456. So that is page number 72. See here. The nominal shear stress in beams of uniform depth shall be obtained by the following equation. So tau V equals VU divided by BD, where VU is shear force due to design loads, B is breadth of the member, D is effective depth. So in our case VU, it is 120 into 10 power 3 shear force. So width of the section 200, effective depth of the section, it is 443. So tau V, so it is 120 into 10 power 3 divided by 200 into 443. So tau V will be 1.35. So it will be 1.35 Newton per millimeter square. So this is the first step. Next, second step will be maximum shear stress. Maximum shear stress. So for which you can refer IS 456 2000, page number 73, table 20, or either you can refer SP16 page number 175, clause same 4.2, or you remember the table J. So I will check with IS 456, page number 73. So you have table 20, maximum shear stress tau C max. It is in Newton per mm square. In our case, grade of concrete it is M25. For M25 grade of concrete, tau C max is 3.1. So tau C max equals 3.1 Newton per mm square. So this is for M25 grade of concrete. Okay. So in the next step, in the next third step, we shall calculate the PT, percentage of tensile reinforcement. So we provided AST as 800 mm square. We will convert this to PT. So PT provided it will be so AST divided by BD. So your AST is 800 divided by B, width of the section 200 into effective depth 443. So let me solve this. So 800 divided by 200 multiplied by 443. So it will be I think you need to multiply this by 100. Multiply by 100. It is 0.90. So percentage of steel provided 0.90 percentage. So in the next step, we shall calculate tau C. So to calculate tau C, you can refer IS 456 2000, page number 73. Page number 73 and table 19. So table 19, design shear strength of concrete. So tau C is nothing but design shear strength of concrete. So you have M25 grade concrete and you know the PT. In your case PT is 0.90. So 0.90, it falls in this range 0.75 and 1. For 0.75 tau C it is 0.57. For 1 it is 0.64. So let me copy the readings. For percentage of steel 0.75, tau C it is 0.57. In our case PT is 0.90. You need to calculate this tau C. And next value is 1. For percentage of steel 1, your tau C is 0.64. So this column it is PT and this column it is tau C. You call this as x1, x2, x3, y1, y2, y3. You can use the formula for linear interpolation. So y2 equals, what is the formula? x2 minus x1 multiplied by y3 minus y1, y3 minus y1 divided by x3 minus x1, x3 minus x1 plus y1 plus y1. So this is the formula for linear interpolation. Or you can calculate the tau c by using the calculator. So just I will do it by using calculator. So first mode, go to statistics 3 and you select 2. You just feed the table 0.75 and 1, first column. So second column will be 0.57 and 0.64. Okay. Next you press on. Next you press shift 1. So you select regression. So 5. So you need tau c for this 0.90. So here you type 0.90 equals. So it will be 0.612. So your y2 will be 0.612. So y2 is nothing but tau c. Tau c is 0.612. So unit will be Newton per mm square. Newton per mm square. So here in our case, tau v is greater than tau c. Clear? So tau v value 1.35. It is 1.35, which is greater than tau c 0.612, or tau v is less than tau c max. What is the tau v value? 1.35, which is less than tau c max. What is the tau c max for M25 grade concrete? It is 3.1. 3.1. So if you are getting these two cases, design the section for shear. Design the section for shear. You can proceed for shear design. If otherwise, if tau v greater than tau c max, if it was the case, then you need to revise the section. You need to revise the section. Clear? Next, in the next step, I think it will be step number 5. So we will be calculating VC. What is VC? It is nothing but shear taken by concrete. Shear taken by concrete, for which you need to refer IS 456-2 2000, page number 72, and class 40.4, or either you can refer SP16, page number 175, page number 175, class 4.3. So VC, we have the formula. So let me open IS 456 first. On page number 72, I think page number 72, yes. So it is tau C BD. So VC, it is calculated as tau C BD. So VC equals, your tau C is, what is the tau C value? 0.612. 0.612 multiplied by width of the section 200, effective depth 443. So 0.612 multiplied by 200 multiplied by 443. So it will be 5422.3.2 Newton. So you divide it by 10 power 3. So it will be get converted to kilonewton. VC equals, so it will be 54.22 kilonewton. So this is the shear taken by concrete. So next we shall calculate Vs. It is shear taken by stirrups. Shear taken by stirrups. So we have the formula Vs equals, if you open the code, so Vs equals Vu minus tau C BD. So here formula is Vu minus tau C BD. So shear taken by stirrups, it is Vs equals Vu. Vu, you have 120 kilonewton minus tau C BD value. It is nothing but your Vc, 54.22 kilonewton. So your Vs value, 120 minus 54.22. So it is 65, nearly equal to 66 kilonewton. So this is your Vs. So next, step number 6, we will calculate for vertical stirrups. Vertical stirrups. Same, you refer IS 456 2000, same class, 40.4, page number 73. You have the formula for vertical stirrups. So Vs equals, Vs equals 0.87 Fy ASV multiplied by D divided by SV. So this is the formula, 0.87 multiplied by Fy ASV multiplied by D divided by SV. So provide two-legged 8 mm dia stirrups. This is my assumption. I will assume this as my stirrup or shear reinforcement. So for which Vs, it is 66 kilonewton into 10 power 3 Newton. So 0.87 multiplied by Fy. So Fy, it is 415 for shear reinforcement. So Fy, it has to be taken as 415 multiplied by ASV. So here ASV. See here, ASV is total cross sectional area of stirrup legs. Total cross sectional area of stirrup legs. So ASV, I will be using two-legged 8 mm dia stirrups. So this area is two legs. 2 multiplied by area of one leg. It is pi d square by 4. So 2 into pi into stirrup diameter 8 mm. 8 square divided by 4. So 2 into pi into 8 square divided by 4. So it will be 100.53. So ASV, it is 100 mm square. So ASV here 100. Effective depth, it is 443. So divided by SV. Here you need to assume 1 and find 1, for which I assumed ASV. I am using two-legged 8 mm dia vertical stirrups. So ASV comes out to be 100 mm square. So I will assume ASV and I will find SV here, which means spacing. So your SV will be, so just you interchange it, 0.87 into 415 into 100 into 443 divided by 60 into 10 power 3. 60 into 10 power 3. .87 multiplied by 415 multiplied by 100 multiplied by 443 divided by 60 into 10 power 3. So it will be 0.87 415 100 into, sorry, 60. This is not 60, this is 66 here. So this value is, it is 66. I have interchanged these two terms. I have taken this here and this SV here. So SV spacing comes out to be, so here it is 66. So 242 millimeter. So I will provide two-legged 8 mm dia stirrup at 225 mm center to center. So this much I will provide. Even though I have got the spacing of 242, but I will provide the spacing 225 mm. So you please remember, shear spacings will be provided in multiples of 25 mm. So you please remember this. shear spacings will be provided in multiples of 25 mm. So either you can provide 225 or 250 or 200, like this. The spacings will be multiple of 25 mm. Clear? So next, whether whether the reinforcement provided, it will be satisfied minimum shear reinforcement requirement. We need to check that also. I provided two-legged 8 mm dia at 225 mm center to center, whether it has satisfied minimum requirement or not. So my next step will be, so step number 7, minimum shear reinforcement. So for which you need to refer IS 456 2000, page number 48. Page number 48, clause 26.5.1.6. So let me open the code. So page number 48. So minimum, so clause 26.5.1.6, minimum shear reinforcement. Minimum shear reinforcement in the form of stirrups shall be provided such that ASV divided by BSV greater than or equal to 0.4 divided by 0.87 Fy. Okay, so you just copy the formula. So what is the formula? ASV divided by BSV, it should be greater than or equal to 0.4 divided by 0.87 Fy. So just I will rearrange the terms. So ASV divided by SV greater than or equal to 0.4 times B divided by 0.87 Fy. Just I have taken B to this side. Okay, so this is my left hand side. It should be greater than right hand side. First I will calculate left hand side. So left hand side, it is ASV divided by SV. What is the ASV? I used 100 mm square because I provided two-legged 8 mm dia stirrups. So ASV will be 100 mm square. So spacing SV, I provided a spacing of 225 mm. So it will be 100 divided by 225. So it will be 0.4. Next I will calculate right hand side. Right hand side, it is 0.4 times B divided by 0.87 Fy equals, so 0.4 times width of the beam 200 divided by 0.87 Fy. Fy is 415. So let me check this. 0.4 multiplied by 200 divided by 0.87 multiplied by 415. So which will be 0.22. 0.22. If you compare these two, so LHS and RHS. LHS is 0.4, RHS is 0.22. So LHS is greater than RHS. Hence, whatever the shear reinforcement provided, it has satisfied the minimum requirement. Hence, it is okay. So I will provide two-legged 8 mm dia at 225 mm center to center. So this has satisfied minimum requirement. Okay. So next step will be, so what is the step? I think step number 8. So we need to check spacing of shear reinforcement. Spacing of shear reinforcement, for which you may refer IS 456 2000, page number 47. Page number 47, clause 26.5.1.5. So page number 47. Yes, maximum spacing of shear reinforcement. See here, the maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 times D. So first criteria it is 0.75 times D. So we shall check second criteria. So second criteria will be, in no case shall the spacing exceed 300 mm. So 300 mm. Next, third one will be calculated spacing. So third one will be calculated spacing. So 0.75 times D. So your effective depth will be, I think it is 443. So let me check the effective depth. Effective depth is 443. So 0.75 multiplied by 443. It is 332 mm. 332 mm. So second one will be 300 mm. So third one will be calculated spacing. So calculated spacing, initially it was 242 mm. So you need to provide whichever is lesser. Whichever is lesser among these three. So lesser will be 242. So but I provided SV 225 mm. Hence it is satisfied. So this is how you can use IS 456 for design of beams for shear. Now we will discuss SP16 method. Now we will discuss SP16 method. So for which we know the Vs value. It is 66 kilonewton. So shear taken by stirrup. Shear taken by stirrups. So Vs. Yes, it is Vs 66 kilonewton. Next, effective depth 443 millimeter. So convert this value to centimeter. So divided by 10. So 443 divided by 10. So it will be 44.3. 44.3 centimeters. Next, you calculate Vs by D value. So your Vs is 66 kilonewton divided by D is 44.3 centimeter. So it is 66 divided by 44.3. So it will be 1.48. 1.48. So unit will be kilonewton per centimeter. So let it be in kilonewton per centimeter. So now you refer SP16 page number 179, table number 62. So let me open SP16. What is the page number? Page number 179. Yes, 179. So I'm in the same page, 179. Table 63. Bent up bars. Values of VUS for single bar. So here Fy 250. Here Fy 415. I am using vertical stirrups. So alpha will be this one, 45 degree. I think table 62. Yes, this table 62. So shear vertical stirrups, values of VUS by D for two-legged stirrups in kilonewton per centimeter. So first you have Fy 250, next column will be for Fy 415. Your diameter, stirrup diameter, it will be 8 mm. You are using 8 mm dia stirrups. So your VS by D value, it is 1.48. You are using 8 mm dia stirrup. 8 mm dia stirrup, and your Fy, it will be 415 Newton per millimeter square for shear reinforcement. So now you can refer table 62. First Vs by D value, it is 1.48. So 1.48. So it will be in between these two values, 1.452 and 1.815. So for 1.815 spacing will be 20. For 1.452 spacing will be 25. See here. First initially 1.452 for which spacing will be 25. So you need 1.489. Yes, so this value it is 1.489. So for 1.489 what is the spacing? For 1.815 so spacing will be 20. So this column is Vs by D value in kilonewton per centimeter. So this will be spacing in centimeters. Here same it is x1, x2, x3. This is y1, y2, y3. I will use the calculator. So first mode statistics to 1.452. Next will be 1.815. For 1.452 25. Next 1.815 it is 20. On shift 1 regression 5 1.489. What is the spacing? 24.49. So your y2 it will be 24.490 centimeters. So this is your SP. So you convert centimeter to millimeter, multiplied by 10. So it will be 244. 244.90 millimeter. So this is the spacing you require. But you provided the spacing. So your final conclusion it is provide two-legged 8 mm dia stirrups at 225 mm center to center. In SP16 method also you arrived the spacing of 244. In IS456 method, spacing you arrived the spacing of 242. So either you can go with IS456 or SP16 methods for design of beams for shear force.